Hello everybody, this is the first lecture of week 3, and today we're going to talk about conditional probability and how that leads to a rule for how to compute probabilities of intersections. So basically, in order to do this, we're going to define another concept, and that is the vertical bar. So we're going to let probability of A and then this vertical bar B mean the probability of A occurring given that B has occurred. So this vertical bar means given. Basically that means that on this side of the vertical bar, our probability rules govern or apply. And the other side is just given information, background information. So as far as the rules are concerned, you only have to worry about what's going on to the left of that vertical bar. Everything on the right of that vertical bar is just information to inform the probability calculation. Well, how do we get probability of A given B? If we're given that B has occurred, then we know that our dart has landed somewhere inside this region here, inside B. So B basically becomes our new sample space. And if we're looking for the probability that A occurs, given that we're in that sample space, we have to look at the area of A inside B. So the probability of getting into A, given that B has occurred, is going to be the area of A inside B, which is this region here, divided by the total area of B. It's just a simple ratio of these areas. As that area gets smaller, probability of A occurring gets smaller. Well, that area inside A and B is just probability of A intersection B. And of course, the area inside B is just probability of B. So I can rearrange this equation here to develop an expression for probability of A intersection B. And that's shown right here. Probability of A intersection B is probability of A given B times the probability of B. And this first part is a conditional probability. Probability of A given B, and typically conditional probabilities are more difficult to determine than our total probabilities of B. So in order to estimate the probability of B, I just have to repeat an experiment many times, count out how often B occurs, and then divide that number divided by the total number of trials. But the probability of that A occurs given B, I've got to look at just those where B occurred and then count up how often A occurred, what the relative frequency of A occurring was. If B is relatively rare on its own, we may have very few A's occurring inside there, and so this probability here can be either highly inaccurate or maybe we can't get it at all. So conditional probabilities are typically more difficult than these total probabilities. Well, the other thing we can note is that since A intersection B is the same as B intersection A, I could just flip all these A's and B's around and I get the following expression. B intersection A is probability of B given A times probability of A, and that must just be equal to probability of A given B times probability of B. Well, this gives us another relationship that allows us to solve, for example, for probability of B given A in this following relationship. Probability of B given A is equal to probability of A given B times probability of B divided by probability of A. And this leads to something, a very famous theorem attributed to Bayes that can be used to, we generally use it to flip these conditionals around, but another way of using it is to say, okay, if I gather some more of information A, what is my updated probability of B? And this is a very powerful use of this Bayes theorem. We have an original probability of B taking place. I've gathered some information. I can use this weighting here to figure out a new or updated probability of B occurring. Okay, so let's you look at some examples illustrating this. We're back to our bin of network cards, of which 5 are defective. If 2 network cards are chosen at random, what's the probability that neither will be defective? Well, we just saw that example, and we solved it there using counting principles. And now let's use probability rules to solve that. Let's let D sub I be the event the ith card selected is defective. Then we want to find the probability that D1 complement and D2 probability of D1 complement and D2 complement. In other words, probably the first card selected is is non-defective and the second card selected is non-defective. So we could do this in two ways. We know a rule now for an intersection, so it's the probability of D1 complement given D2 complement times the probability of T2 complement, that's the upper one, or we could flip them around. It's probability of D2 complement given D1 complement times the probability of D1 complement. The problem with the first form is that it's given that the second was non-defective, and that's not usually the way we would do this. We usually would know about the first, and we're trying to figure out what's the probability of the second. So this way is better. Probability of D2 complement given the D1 complement, that the first card was non-defective, and then multiply by the probability that the first card is non-defective. So we're going to use this form of this probability rule. By the way, I forgot to mention way up here that this rule says that for each intersection we get a multiplication. Okay, so probability of A intersection B is the product of two probabilities. And the nice thing about intersections is that it doesn't blow up into more terms. Probability of A intersection B intersection C is going to be the product of three things. Okay, so I'm going to write this: the probability that the second is non-defective given that the first is non-defective times the probability of the first being non-defective. We know the probability of the first being non-defective means that I've selected from the 55 non-defectives, and so the probability of that is 55 divided by the 60 total cards. If I've selected one of those as being non-defective, and I've done that here, so I've taken out one of the non-defectives, I now have 54 non-defectives and a total of 59 cards. So the probability that the second is non-defective is now 54 over 59. Multiply these two things out, and I get 99 over 118 as we had before. So another example is this. A bridge deck is supported by two concrete girders. Failure of the bridge will occur if either or both girders fail. Engineer estimates the probability of failure of a girder is 0.05 and believes that girder failures are due to reinforcement corrosion, and expects a reasonably high correlation between failures, and estimates the probability of that the second girder fails given the first has failed to be 0.7. What then is the probability of failure of the bridge? We know that both girders could fail essentially simultaneously, so we have to include that the probability of that occurring. So let's let F1 be the event that girder 1 fails, and F2 be the event that girder 2 fails, and let's let F be the event that the bridge fails. So we know from the given information that the probability of F1, girder 1, is equal to 0.05, and the probability of F2 is also equal to 0.05. So 5% probability of failure of either of these girders. We also know that we're also told that if one of the girders fail, the probability of the other one failing increases significantly to 70%. So the event F is the event that girder 1 or girder 2 fails. So this is the union of F1 and F2. And so our Venn diagram looks like the following. We've got F1, F2, we could have them both fail. So we've got an intersection between them. So we know that probability of F is the probability of the union of F1 and F2, and our rule for unions is probability of F1 plus probability of F2 minus their intersection. We were told probability of F1 is 0.05, probability of F2 is 0.05. The probability of the intersection we're going to write is probably the failure of the second, given failure of the one, which we know is 0.7. And the failure of the first is 0.05. And so I add all these things up, I get 0.065. Okay, let's look at another example. If we reconsider example 2.21, and that's the one about the pumps, what is the probability that pump A will fail during the design life given that pump B fails? What is the probability that pump B fails given that pump A fails? Recall our Venn diagram looked like this, where FA was the event that pump A failed, FB is the event that pump B failed. So we're looking now for probability that the B pump fails given that the A pump fails. Now, this thing here, we saw earlier, there's another formulation for this thing coming from our original equation. A given B is probability of A intersection B divided by probability of B, so we'll use that form here. because we're directly looking for this conditional probability. FA intersection FB, we know what that is. It's 0.01 divided by probability of FA. We know what that is. It's 0.03 plus 0.01, which is 0.04. So we get a probability, conditional probability here of 25%. Okay, let's look at another example. Let's suppose a single CPU is selected from a box of 10,000 CPUs. 3 different types of defects are denoted A, B, and C are known to occur in these particular CPUs with the following probabilities. Probability of defect A is 0.01, defect B 0.05, defect C 0.0075. Probability that both A and B defectives occur has probability 0.0025. Both A and C occur has probability 0.003, and probability that B and C occur has probability 0.002. Finally, the probability that all 3 occur has probability 0.001 or 1 in 1,000. Now the question is, if both defects A and B occur in a CPU, is the defect C more likely to occur than if neither defect A or B occur? Well, to answer this question, I guess the first, in fact, I highly recommend that your first step is to construct a properly labeled Venn diagram. Once you've done that, a lot of the problems are very simple to solve. We need to identify the probability in each disjoint area in the Venn diagram, so we start in the middle. So we got 3 events, 0, 0, A, B, and C. And we know that the intersection, probability of A, intersection B, intersection C is 0.001. Then we use the other pieces of information given to us. Probability of A, intersection B was 0.0025, and we work our way back out in this picture. Okay, so if we say probability of A, intersection B was 0.025, that we know is equal to 0.001 plus 0.0015. Okay, so we can label that area there as being 0.0015. Probability of A intersection C we know is 0.003, so we've already accounted for 0.001, so this area here must be 0.002. Okay, and probability of B intersection C we know in total is 0.002. We've already accounted for 0.001, so this has to be 0.001 as well. Okay, finally, probability of A we know is 0.01, and that's made up of those 3 areas plus a final area, so 0.001 plus 0.005 plus 0.002, and the remainder has to be 0.0055. Okay, the sum of those 4 numbers is 0.01. Similarly, probability of B, everything inside that circle B must be 0.05, and that's made up of 0.001 plus 0.0015 plus 0.001, and that leaves us 0.0465. Okay, and the probability of C is, we know the whole probability is 0.0075. That's made up of those 3 terms plus 0.035. And finally, if I add up all of those terms shown in red and subtract from 1, I see that outside I've got 0.939. Okay, so there's your properly labeled Venn diagram. Okay, now we want to compute some things. So we're asked, if both A and B occur, is defect C more likely to occur than if neither A and B occur? So we want to compute the probability of defect C occurring, given that both A and B occur, and then compare that to the probability that defect C occurs, given that neither A nor B occur. So let's look at the first one first. We want to compute the probability of C, given that defects A and B have occurred. And let's do that. So C given A and B is going to be the intersection between C, A, and B, so probability of A intersection B intersection C, divided by probability of A intersection B. I know all of these numbers. There's 0.01 is the intersection of the 3 of them. A intersection B comes from our given information is 0.025, and that probability is 0.4. And then we're looking for a probability of A, C, given that neither A nor B occur. That's the intersection of all three of these. So A complement, intersection B complement, intersection C, and that is C alone. That's everything outside of A and B, but including C. So that's the 0.035. And then probability of A complement, intersection B complement is everything outside of A and B. So it's A union B complement. So it's 0.0035 plus 0.939, which we have here, and we get 0.0037. So basically, it's saying that C is much more likely to occur if both the defects A and B occur, and it's by a factor of about 10. Okay, another example. We got a bin of 1,000 switches, 600 are brand A and 400 are brand B. If 10% of brand A switches are defective and 5% of brand B switches are defective, what is the probability that brand A will be defective if a single switch is selected at random? Oh, sorry. If a switch is selected at random, what is the probability that it is brand A and defective? Although strictly speaking, because there are 1,000 switches, this is a counting problem. We have to look at the number of ways of selecting one switch from 600 or one switch from 400 and so on and so forth. But we're only interested in probabilities relating to a single switch selected from the 1,000, so we're going to just deal with this in terms of probabilities directly. So let's let A be the event that the switch is brand A, B be the event that switch is brand B, and D the event that the switch is defective. Then for a single switch selected at random, probability that it's brand A is 600 over 1,000, so 0.6. Probability of brand B is, of course, 1 minus that, which is 0.4. If it is brand A, the probability of it being defective is 10%, which is 0.1. And if it's brand B, probability of defective is 5%, 0.05. And we're looking for a probability of A and D, so it's brand A and it's defective. For this case, we can just directly use our rule for intersections. Probability of A intersection D is probability of D given A, which is what we have up here, times probability of A, and we have that as well. If I had written this as probability of A given D times probability of D, I don't have that information given, so I have to turn it around and use it this way. But I know these numbers, so probability of A and D is 6%. And that ends this lecture.